I gotta shift the camera. All right, so live again. I'm going to move this a little bit. Not that way. This way. Okay. Someday, there we go. That's good enough. If I get, now I'm not begging for subscribers, I'm not that kind of person. However, at this point, I might want to because I want to be able to use my phone and I can't. Staging is everything, people. Okay. Can you see Kim? Ooh, it's a little, oh no. Hang on. Tip it up. There we go.
How many subscribers?
I need 1,000, so 1,000. I have 720, so I'm close. So anybody out there, and I can do this with my computer sitting over here, and then I can show you stuff. But right now I can't use my phone. I'm not cool enough. Help me be cool enough. Wait, here we have Mr. We have a teacher here that drinks a lot of coffee, and he's cool. So. Okay, turning Mr. Electrohand. Okay, shout out Mr. Electrohand. Okay, so here we go. We're going to do quantum theory. We are going to add a little bit of quantum numbers, even though they're not on the AP exam. Hear me now. Quantum numbers are not on the AP exam, but quantum theory is. Okay, so I think it's important, though, that you know that every electron has 4 quantum numbers unique to it. Okay, and this is how the electrons organize their atoms, organize their electrons. So it's just bookkeeping. Some people use like analogy like filling a hotel. So you get a bunch of guests and you fill them in the best rooms first, and then you kind of give them the rooms later that are not as good. I have a wonderful student teacher has an analogy where he has like a palace that he was filling, and it's pretty cool. So hopefully your first year chem teacher did something fun when you did electron configurations, but they might not have. So I have students behind me that are watching. I won't name them all again because they got embarrassed. They hopefully will ask questions loud enough that you can hear. And hopefully if I ask them questions, they will answer. But I have one, Aaron, staring at me like that. Okay, so we are here now it's 9, okay, but it's 9 a.m. These kiddos could have slept in. Wonderful people came here to study for AP Chem. Our freshmen are being tormented with a state test. Love it. Freshmen should be taking tests. And then they have had other tests that they had to take before. So they're getting ready for their AP exam. Here we go. Quantum theory. Off we go. So my students have a lot of notes for this already, but if you don't, I'm going to start from the very beginning of the story with lots of colors, I hope. Okay? Actually put these at the ready here. All the colors. And then I'll slide this off the screen because that looks gross. Okay, so you have atoms. Atoms have electrons, they have protons. Now the protons we need to worry about a little bit, but really it's where the electrons are. So quantum theory is a theory about really where are all of the electrons in the atom. And it's not only about where they are, what energy do they have, and kind of what kind of motion and movement do they have in the atom. Okay, so we're going to start with our tiniest little atom we've got on the periodic table, which is hydrogen. Okay, so what I'm going to do is kind of divide this into 2 sections. Over here, I'm going to have a little atom that's going to start out kind of small. There's my nucleus. It's okay if you can't see the nucleus because it's supposed to be really small. Most models of atoms out there are ridiculous. They're all got a nuclei that's way too big. So I put it's right here. If you lose sight of it, that's okay, because it's a small amount. Right now, it would have 1 proton right there if it's hydrogen, and there's an electron that's going to stay as close as it can, but it's going to move around that, the outside space. So I'm going to start with, let's just use red, okay? So the electron for hydrogen might be moving around in a 3-dimensional shape around the center, focusing closely towards the nucleus where the proton is. And then what happens is this makes an orbital. Okay, I'm going to draw it with a shaded border, even though it's not, so that you can see that it's 3-dimensional. And they found that if they wanted to find the hydrogen's only electron, it would be close to the nucleus, but it would be in a spherical pattern. And more times than not, it would be there and not here. It's called an orbital. It's a 90% probability of finding the electron. Okay? So This is going to be over here. I'm going to label it as my, way down here. Hopefully you can see this. Let's go way over. Well, let's go about right here. 1s. Okay? So what they'll do is they'll say this is the orbital. So if you want to put words, you can. I'm not going to put the word orbital, but you probably should in your notes. This is the orbital. It makes a spherical shape. That's not really why it's called S, but we'll lie and say it is. Okay? And so then what the chemists do is they will put, in fact, I'm just going to do it this way with black so it's easier to see. They will draw an orbital diagram. You should write that down too, orbital diagram or orbital notation. And what they'll do is they say this electron is like an arrow, and they'll put it facing upwards or down. Most of the time we just start up. You can do double-headed arrows or one-headed arrows, which is lazier. That's what I do. Okay. The other thing you're going to see is some teachers will have this as a box. I will be honest with you. I'm too lazy for a box. Okay. So I'm not doing the box. And some are circles. Okay. I'm just okay with the line. What that line means is there's only one 1s orbital. Okay. Next, that would be hydrogen. So over here, what I'm going to do is say, what is hydrogen's configuration? So I'm just going to put H. And I'll just put it in red. It's 1s1. Okay? It has one valence. So way over here, you can put the valence number too. I think that's all on the screen. Looks good. Okay, next, really fast, because my students should have these notes already, but you might not. And I have a wonderful student. I talked about him before, Josh. He is learning this sort of for the first time. He's a new addition to our school, and his first-year chem teacher didn't cover this. It's not exciting, so I see why they would skip it. Okay, moving on. But it's important. So the second electron is going to fit in that same spot. So when you go from being hydrogen to helium, or an atom has 2 electrons, okay, helium has 2 electrons, 2 protons. It has neutrons. We won't even talk about them. So you have 2 electrons. It's going to put both of those electrons at the first energy level in that same spherical shape, but it's going to have a 2. So it just is telling you 2 electrons making a spherical shaped orbital in the first energy level closest to the nucleus, and then it has 2 valence. And then over here, I'll have to make more room later, and I'm just going to go left to right here. You would draw 2 arrows. This is called Pauli exclusion principle. So the Pauli exclusion principle says that if your electrons are paired in the same orbital, they have to spin opposite. Okay? Right away, I'm going to do quantum numbers immediately. Okay? So here are some of the quantum numbers. The energy level is called N. So I'm going to see if I can sneak that way over here. Okay, and the energy level can have the numbers of 1, 2, 3, out to 7. Okay, so that's your first quantum number, and that is off the screen. Sad face. Oh, there. So N is 1, 2, 3, 4, 5, 6, 7. So what you would do is you would say right here, I'm just going to draw like a little arrow, a little squiggly arrow. Okay, this one right here has a first quantum number of 1. Remember, these quantum numbers are not on the AP exam, but I think they help a student that's an AP who should have learned this in first year chem make a lot more sense of what's going on. Okay, first energy. So with this one here too. Okay, so both of these would have a quantum number of 1. The first quantum number. Second quantum number is called L. This is the orbital. To keep it simple, it's got a name, but I don't care what the name is, and nor should you at this point. It's like the orbital type, okay? Now, the problem is the orbital types are S, P, D, and F, and those are not numbers. They're letters. So, Josh, you ready? Hang on. And my students, they might not know this, or they might know this. I don't know. S is the 0, P is a 1, D is a 2, and F is a 3. If you had another orbital, you just keep on going. After F, starts to go alphabetical. So then you have G, H, I, J, and the numbers just keep going, okay? So for us, our second quantum number is going to be 0 for all of these, okay? So all these, these electrons, and this electron and this electron are, we'll say are kind of similar. That's their second quantum number. Oop. Yeah, no, we're good. All right, then, if you want, we could just skip this one if it's confusing. I'm actually just going to skip that one. We can just say it right there. Then the next number is called M sub L. It has a name, But what I'm going to do is just say it's sort of the 3D orientation of the orbital. Now, this is where life gets a little tricky. So S orbitals, there's only one possibility. They are spherically shaped. You only can have that. Now, P orbitals are kind of a dumbbell or a butterfly shape, or not butterfly shape, a dumbbell or a figure eight. And they can face 3 different directions. So a lot of times people will call this the PY, PX, and PZ. That's what I mean. So however you want to label that, that's the M sub L. And we got to give those, again, numbers. I'm going to pick on Richmond because those are letters, right? PX, PY, PZ are all letters. So to make a number out of it, you would do this. And you can arbitrarily pick whatever you want, but most people do -1, 0, and +1. Now, here's the trick. M sub L goes from -L through 0 to +L, okay? So because M sub L was for P1, this is going to go really fast. It's okay. We have 3 choices, and we're going to give them a number. Now, for an S, M sub L would be -0 to 0 to 0. So when you have something like an S orbital, you would say that the third quantum number is just 0. This is where the problem lies. This is where Pauli, Wolfgang Pauli came in and said, they're the same electron at this point. So they have to have something different. So they're going to spin opposite. The last quantum number is M sub L, and it's the spin clockwise or counterclockwise. So, in first year chem, you might have just drawn something like that, but they had to give it a number, and they used a fraction. Why? My guess is because a half plus a half equals 1, and it's a whole orbital. Okay. Might be kind of a lie, but I'm going to go with it. I don't think Mr. Carlson. What do you think? I don't know. Why they picked a half? My guess is that when you add them together, it equals 1 orbital. I don't know. What do you think, Megan? Let's just go for it. It's fine. So what we're going to do is say this one's plus a half, and this one's minus a half. And together they fill that 1 orbital. Now they have unique 4 numbers, okay? So let's keep going to bigger atoms. So that is the most you can put at energy level 1 in the S shape. So what you might want to do somewhere is have a list of what's possible. So they go in this order: 1s, 2s, 2p, oh, little s here, not big s, 2s, 2p, 3s, 3p, 4s, yes, 3d, we'll talk about that later, then 4p, 5s, so my students check if I make a mistake here, 5s, 5p, I missed 4d, 4d, they caught me 5p, 6s, be careful, 4f, talk about that in a little bit. Then we have 5d, 6p, 7s, 5f. What did I leave just enough room? 6d. Where would it go? We don't have one of those yet, though. Okay. So the largest atom we have on the periodic table fills its 7p6. I can't say this guy's last name, so I'm sorry. Yuri Ognesia. It's called OG. Okay, so I'm just going to get rid of the 8s. That's where we're going to go next, but we're not there yet, so let's ignore it. Now, be careful. When we get to some of these, you can put more of electrons in certain orbitals. So, for example, I'm going to get rid of these quantum numbers. Hopefully, you wrote them down. 1, 2, 3, they're gone. Okay, you can always pause the video and go back. But we're going to have a 1s, and the next one is going to be a 2s. After the 2s, you're going to be possibly having a 2p. So I'm going to just push these all together to save room because I only have this tiny screen I can put on here for this. And then the electron configurations are just going to have to get kind of pushed over here. Okay, so like I'm just going to have to put the hydrogen here was 1s1, 2s1, and then when we 2s1, what am I saying? 1s2, 4, and they'll put the labels on this side then. As far as lithium, right? Yeah. As far as valence, you're just going to have to add that yourself if you can sneak it up to the side. All right, so the next electron containing, or multi-electron containing atom, that's the way to say it, multi-electron containing atom is lithium. So lithium has 3 electrons, so it will give the electrons sort of the best place in the house, so the electrons will be tend towards this position, which is 1s 2. Then there's a third one. So what I'm going to do is just use green. Okay, very Christmas color here. So it has to go to another energy level. So let's say this is energy level 2. Okay. And then there are what are called nodes or dead regions where it can sneak in there, but really it kind of stays out and moves around the atom like this. Here's the center. Here's your what's called the 2s electron, and it's going to have a spherical path. It's going to move in just a plain old, like a beach ball shape. It's a simple sphere at energy level 2. Now, in reality, it's actually like not a beach ball, but an inner tube. So there is an area in the center that it's like, I can't go there because there's some electron repulsions in there. So it kind of stays away from there. You don't have to worry too much about that, though. So I'm going to say that third electron will occupy a 2s orbital, and it'll be in that space. Okay, so then you would say over here, 1s2, 2s1. So that's what that configuration is coming from. And now I want to slide these even over more because we're going to fit more. The name of this is called the Aufbau principle. It's German for build up. So I have to keep making more room because we're going to have to keep building up everything. So if I keep sliding stuff, just deal with it, okay? So we're going to move across here. All right. How are we doing, Josh? Good. Good. Okay, there's Josh. You can hear her. So the next multi-electron containing atom is, let's just see it because they are so quiet, just to know that they're there. What electron containing atom is next? Beryllium, they said. They didn't say it loud enough. Beryllium. Okay, Be, right? How many total electrons for beryllium? 4. In fact, sometimes you'll see what down here. It's not the number of electrons, but it kind of is. What is that we put down in the bottom left called? Atomic number, okay? But it's number of protons, and right now they equal the electrons. We are not removing electrons, no ionization energy, no electron affinity at this point. We're going to stay with, 3, 2, 1. There is a number up here, which would be called the mass number, and that's to find out how many protons compared to neutrons there are. So for beryllium, it's common that it's, I think beryllium is 7. I think that's a common one, or even 8. That's the mass number, and when you subtract these two, that's how many neutrons there are. But usually on AP Chem, we don't worry too much about the neutrons. I'm just going to skip that. So we'll have to have 1s, 2s, 2p, maybe, but maybe not. Okay, you're going to fill the lowest energy orbitals first. So the Aufbau principle says these are the lowest and these are the highest. I made a session 1 video where we talked about PES or photoelectron spectroscopy, which will prove that those are the more tightly bound electrons and they want to stay closer to the nucleus because they're more tightly held. Okay, moving on. We're going to say it has these two, and it has a third, but it also has a fourth. And we're going to fill these lower energy orbitals first. They have a more energetic, favorable position there. So all you're doing is adding another one in there. Moving on. So over here, slide this one over, 1s2, 2s2. And then the periodic table kind of has a part where it stops, okay? And then there's a big jump to the other side. That's because for the next multi-electron containing atom, you're jumping over to what's called the p block, okay? So beryllium goes to boron, then carbon. Let's just list them out. Then nitrogen, oxygen, fluorine, and then we're back at it again with neon. Look at neon, and then we're back to sodium. Okay, so we want to make sure we kind of get to here, and we can keep going. I'll have to erase that, so at some point make sure you write that down because it'll be gone, or pause the video. So let's keep going. What happens now is because the second energy level with the S shape is filled, it does move on to another orbital. Now, you're going to see this in your book somewhere. I'll put it right here, and it'll have to get erased. But at every energy level, you can gain, and again, don't worry about why. In AP Chem, I would say just this is true. It's fine. You can prove it later if you get a Chem major. So 3s2, 3p, and then you can have a 3d. Now, it doesn't fill that 3d as you saw. It fills the 4s before the 3d, and that has to do again with energy. So just deal with that. But at every energy level, so this is energy level 1, 2, 3, at energy level 4, you can have 4 possible orbitals. So you can have a 4s, 4p, 4d, and 4f. At energy level 5, you can have a 5s, 5p, 5d, 5f, And this is where people are excited about the G block, okay? If it's going to happen and where it's going to go. That is a whole new area of science that some people are really focusing on. Is there's a prediction that we could get to what are called G orbitals, okay? There's also this island stability, which is way beyond what we need to worry about. But that's if you're really interested in science. So once you get to the 6th energy level, you just keep going. So that's one of the quick ways to know, like at every level of energy level, you can gain another type of orbital. Be careful though, you also gain more options. So let me just cover this really quickly. If you had a D orbital, they make kind of like a butterfly looking shape like that. There are 5 of these. So they face in different directions. And then there's this one that is like three-dimensional. And then there's one that looks like this, which goes back. And then there is this, we always call it the strange one, okay? Just the way it is. There are 5 d orbitals, and you'd go -2, -1, 0, +1, and +2. You can also call them dy, dy, it doesn't matter. The big 3 becomes that you know that there's 5 possibilities, okay? So when we start to do d orbitals, you'll have 5 of those lines or 5 of those squares, okay? Moving on. So let me get rid of this. It's going to have to go away because I could keep it actually for it. So here's my first energy level. Here's my second. Now my students know this. You can prove this with an equation of orientation. The third energy level is not equally spaced. It actually is closer to the second than the second is to the first. You will see that on a lot of tests where when you talk about electrons moving between levels, there's a big gap between the first and the second level, but as you go the 3rd, 4th, 5th, between those, they start to get crunched up. Where that comes into play is when you have electrons moving between levels, flame tests, emission spectrums. So I don't know if I'll cover that, but I'll try. Josh, have you heard of that stuff? Oh, we might cover it, okay? So when electrons move between these, be careful. A 3 back down to a 2 is not the same as a 2 back down to a 1. I don't know if that makes any sense, but it's not the same packet of photon energy. The 2 to 1 is actually a big packet of energy, whereas the 3 to 2 is less, okay? And then 4 to 2 will be even smaller. So be careful that they both only have, 1 change, but this is a bigger energy. Okay, let's keep going. Orbitals, how we fill them up. So we're going to go to boron. It's going to have a 1s, 2s, 2p, the 3 possible orientations for the p orbital. And what we're going to do, I'm just going to color code for a while. 1, 2, 3, 4. So this 5th electron, let's say we'll call it 2, okay? It ends up in a new orbital, okay? And again, there are some node regions, but it's only going to go out to 2 and move around in this figure 8 or dumbbell shape. Again, it has a hard time trying to sneak into this area, but it ends up making most people still draw it like this, okay? All right. So that's where this electron is located. Let's quickly do quantum numbers for it, even though they're not, again, on the AP exam. Here we go. So this is the part that my students that are really good at this, this is sort of their new thing, not on the test, but I do agree most colleges add this into their curriculum. So here we go. So this one, let's just practice the quantum numbers for it. You have to have 4 unique numbers. Number 1, energy level 2. Okay, so I can hear my students saying it as I predict the next one. It is a P shape, okay? So that's the energy level. P's are going to be a 1, okay? Then you keep going. You can pick whatever you want, really, but most people do. You can do -1 first, okay? Or 0 or 1. It's arbitrary at this point. Then we'll just say most of the time students do +1/2. So that's its set of 4 quantum numbers. We'll do that again when we have another one or a partnership to that one, okay? All right. So I'm going to keep going much faster. I do have to get rid of this up here, so make sure you have this somewhere, because I'll probably reference it and I'll probably point here, but it's not going to be here anymore. All right. So this is where we have another rule. It's Hund's rule. I think it's EL Hund. I don't know what it stands for, but I think it's EL Hund. That looks weird. See, now I'm being picky. 1, 2, 3. So what'll happen with let's do this. 1s2, 2s2, 2p1. This one's going to be, this is off. Okay, so then carbon's right here. Carbon. go back to those later. We've got 1s2, 2s2, 2p. What do we predict? 2p2, right? So let's just do that first. Carbon is how many electron containing? Should be 6, right? So we have our first electrons in energy level 1 in that sphere shape. Your second 2 electrons after that are going to stay at energy level 2, making a lower, lower energy, more tightly held S shape. We're going to have an electron here. That's the 5th. This is where things get different. So it's Hund's rule, Hunds, Hund's rule. And what happened was they found that these electrons, when there's another possible orbital, they'll kind of choose it. And it's the same shape, but it is another orbital. That's where a lot of students and some chem teachers make mistakes. That is another orbital, okay? And it's the same shape, but it's still another orbital. So that's going to be called the 2p, maybe you want to call it the 2px. And the electrons moving around, we'll call that this one right here, okay? It's still going to go up. Most books, I think there's an argument out there, but we all believe they pair, or that when they pair, they all spin the same first, and then when they pair, they spin opposite. Okay, so we're going to still put that one up. And then let's just quick do a quantum number for that one. 2, 1. Now, we already used -1 last time, so what do we do this time? 0 or +1, but we'll do 0, make it easy. And then because it's still spinning up, we'll say +0.5. So again, quantum number is not an AP exam. I still believe they're extremely helpful to really say, I get it, it makes sense. So let's keep going. I'm going to pick on Josh again. He's just going to say, but I'll just check. Josh, are we good? Yep. Okay, good. It's all brand new to him. His mind, somebody will probably screen capture that right there, and I'll find it on my Twitter or something. Here we go. 1s2, 2s2, 2p. We're still going to apply Hund's rule, though. Carbon 2. Oh, Michelle, nitrogen, right? Yep. Okay, good. So I'm just going to predict it because I think we're getting good at this. Now, this is something, too, that I've seen, and I would just say stop it. I'll ask my student teacher, too. We put the electron count as a superscript, not a subscript. I don't know who does it, but somebody's doing it. Let me show you what I mean. So right here, I see people do this. Okay, they put it down. I think we let students have, because what are you doing? It's probably right. So we're like, stop. Every year, I've taught 20-some years. Every year I have a student who does that, and I've never done it. Well, now I did. Darn it. I gotta watch this video. Don't do that, okay? Josh, is Ori okay with that? Yep. It looks weird, okay? Those of us in chemistry are like, what are you doing? Why are you making subscripts? Subscripts are for, when you make, compounds and stuff. It's crazy. Mr. Carlson, one of these days you'll have to let me know when you teach for 20 years, how many times you've seen that, and you're gonna be like, I never did it, but they do it. I don't know why they do it. We're gonna use purple. So this last electron is gonna be in a D, not a D, what am I saying? In a Z, not D. That's what happens when you do live. You say stuff that makes no sense. So that's the D, or not the D. That's the P, Z, we'll say, okay? Quickly, I know I can hear Ashley over here. She's got it. 2, 1. Oh, now she's quiet. 1. So we use 2, 1, and then we already used technically -1 and 0, so we can use the +1, right? And then still +0.5. So think about what their partners are going to be in that orbital when they pair. They're going to have the same 3 numbers, but then the last number is going to be the downspin, which will be -0.5. Okay. All right. So I'm going to get rid of that again. We don't have room for that beautiful quantum number stuff. Here's the good news. We can keep going. We can Aufbau onto oxygen, then fluorine, neon, and then sodium. Sodium's going to be at the top. Okay, here we go. So we've got 1s. And most of the time, I'll be honest with you, you'll see these going this direction. And then usually if you have a really fantastic teacher, they'll even space this stuff kind of correctly. So there'll be a big gap here. And you'll be like, what's with the big gap? Especially if you got you like it to look the same. It's supposed to be a big gap. They're trying to show you that there's a big gap between here to here. And then they're trying to show you that there's a tinier gap between, of course, the difference in the orbitals choices. And then again, there should be a gap, but it shouldn't be as large. Okay, so then you 3S and 3P. So for most books, this is what you'll see. And when you get to a D, make sure you have 5, and then 4P is all I can fit. And then you might even have an arrow that says energy. I'm going left to right because then I can fit more on the board. Okay, so if any of you are watching this that have a teacher, first-year chem, because not all my students had me as a first-year chem teacher, so their teacher might have done something different. Here we go, Josh. I'm going to have you even kind of predict this one. So 2 here, right, Josh? He doesn't have to say much, just yes. Josh, you doing okay?
Yeah.
Yeah. Okay. And then 2 here. All right. Then how many does oxygen have? So this is 7. This is 8, right? Just through the marker cat. Okay. So then 8. So 1s2, 2s2. Josh, 2p.
4.
There. We're getting Josh to do this today. Okay. Exciting stuff, Josh. Does this make any sense, though, Josh?
I think so.
You think so? That's good. I like that you're a little honest. I think so. Okay, keep going. So we're going to do this. I'm going to start color coding at some point, too. Now, where's the next one going to fill? Okay, so that, by the way, is how many cute little arrows. Arrows are electrons, people. 1, 2, 3, 4, 5, 6, 7, right? But we need 8. Josh, most people will put it in the left one, okay? Can you put it somewhere else? I guess it's just being weird. But some people, I have some students that try to test, can I put it now? Just put it here, okay, people? It's fine. So I just say that there's another electron sharing that same orbital. Now, when that's paired, in the other video, we talked about exceptions to electron affinity. This is when it happens, okay? Because it's the first one to get paired. So that's a different story. But this one has a unique quantum number 2. Let's do this. So let's do both of these 2. 2, 1, 2, 1. Okay. Now what's the same yet? -1. Okay. And then lastly, yeah, +0.5 and then -0.5. You got it. So again, I don't think quantum numbers are hard. A good chem teacher is going to sneak it in there less than 3 minutes, and you're going to go, oh wait, I get quantum numbers. So why wouldn't you add it in? Okay, that's just my opinion. So that's easy. Now, first-year chem students, I wouldn't add that in, but second year, they can handle it just fine, okay? So right now, we're sort of up into here. And you just keep going, okay? So then fluorine's going to be 1s2, 2s2. Josh, 2p? 5, he's got it. 1s2, he's off on like a master here. 2p?
6.
Now things get tricky. 1s2, 2s2, 2p, 6. And now I got to look like what comes next. 3s, and then 1. Okay, so what I'm going to do is get rid of this. I don't have a spot for that anymore. Got to go. And then I got to do 1s. This is where it gets annoying. I have my students do this in first-year chem. It's usually one of the first chapters we cover. They probably go home and think, oh my goodness, what did I get myself into? Okay? But I need you to start getting irritated with this. Okay? Orbital diagrams, as fantastic as they are, they show electron spin. It's easy, I think, to get the quantum numbers. This is getting annoying. I'm going to ask if, Richmond, is this annoying you at this point, all these arrows and lines? You can say yes. It's annoying me, okay? Because there's better ways, okay? So we're almost there, Josh. We're almost to the light at the end of the tunnel where it's like we can shortcut this. But you need to earn the right to do it, okay? So here we go. So I'm done with the colors. I'm not doing it anymore. Okay, so we're going to go 1, 2, 3, 4, 5, 6, 7, 8, and then 9, okay? And then the next one is 1, 2, 3, 4, 5. Hund's rule, people. And pair it with Pauli. Now you have neon with all of the, and again, this goes with this, okay? You got neon with all the orbitals filled, a complete octet. You'll talk about that a lot in chemistry. So then I have to make some room if I'm going to do the next one. So it's 1s, 2s, 2p, and then it's got to have another spot and just one line, because remember, an S only has one option for M sub L. So I've seen people on their charts, they'll have like 0 and then they'll have this. You might have a teacher who even wrote this right on their chart. right underneath it. If not, I've seen some teachers do like, they'll say this is the PY, this is the PX, and this is the PZ. For an S, there is only one way to orient. It's just a sphere, okay? So if I take a p orbital, I'm just going to use, this would be like a p orbital. It works. You can go like that. Ooh, this is why they cost so much. And you can go like that, okay? Whereas if this was just a sphere, I don't have a sphere, let's pretend this. When I orient, I'm just going to pretend here. If this was a true sphere, no matter how I spin it, I don't get a different orientation of it, okay? So again, Y, X, and Z, okay? Moving on. Josh, how are we doing?
Good.
Schmidt, why do you go in order of Y, X, and Z for the
I have no idea. Because I bet you a lot of people do PX, PY, PZ. And it doesn't really matter. You know, as long as you got one of each, and they always have negative and 0, and you know what I mean? -1, 0, and 1. And I hope students are really out there, and I hope mine are, but let's just check for Josh. You have X, Y. I'll blow your mind here, and I don't know when you did this in math, but then, hey, by the way, guys, there is a Z direction, and that's called the world of 3 dimensions, okay? So that's what we're talking about. All right. Thank you, Ashley, for reminding me to do that too quick. All right, so then if I add, let's just add the next color. Let's do, I did orange. I did blue. Green. Pink it is. So really this electron, I'm just gonna put it out here. This is its valence electron right there. This guy, okay? This would have 1 valence. I'm just gonna focus on that. It has more. That would be the electron that again is way out in the energy level 3, moving around the atom in a kind of a spherical shape. However, really it's going to end up being a really skinny, deflated inner tube looking thing. Okay, keep that I think for now. And then, Josh, don't forget it would have core electrons. So there's a point here, Josh. This is annoying, Josh. He's like 2 sips after I say my name. We're going to just call that what it is. All the ones in black, let's just say what they really are. Let me check what's on the screen. Oh, it fits. I'm going to go this way though, okay? Let's just say if I have sodium, neutral, 0 oxidation state, 11 protons, 11 electrons. I don't care about the neutrons right now. We can just say this whole chunk from here to here is neon. I know. Okay, we've been, by the way, again, this is hour 2.
I'm in here.
We're almost done with this one because I'm tired and I need a snack. We had Pop-Tarts, and the healthy snacks are gone. How many Pop-Tarts are left? Nobody cares.
Who cares?
Who cares?
Why are we
So let's just take a break.
5.
And we started with 16. It's pretty good. And I did not give Pop-Tarts to your children. Okay. Now we're gonna have to make sure your mom doesn't see that you ate a Pop-Tart. I know. An illegal Pop-Tart. Okay, 3s1. Yay forwarder called the noble gas core. Okay? Puts the valence on the outside, so we can do that again here. No. Don't cheat, people. Don't be the person who puts neon. Helium, 2s2, 2p6. And at that point, it doesn't save a ton of time putting the helium. Okay. Let's go way ahead. Let's see if Josh is ready. We're going to push him into the big pond here. Here we go, Josh. Let's go to random out of nowhere. We're going to go to arsenic. Okay, so there's a pattern in the periodic table. I have my students actually put all these little configurations, the noble gas ones, these on a big periodic table. It's like, I'm not kidding. I think it's this big. Oh, yeah, let me grab one. Be right back.
I'm folding half to
Got the screen capture too. Okay, so here it is. Look at that size of that thing. These are their periodic trends. It flaps. It's like an airplane. It flaps up and down. So let's not scare people. Let's put those flaps in. Here it is. So they put their configurations on a big table like that. And then on the back is where, if they're my students, they already have, now poor Josh. Okay, we always feel bad for Josh. Hi, Mom. Here is the notes that they've already taken. So they don't, my AP kids don't need to write this down. The only thing they're writing down, like Emma might be writing down quantum numbers. She'll be like, oh, I didn't know that. She added it in. And then this is where I feel, I don't feel bad. I make them really say, Aufbau, are you kidding? And it's not a person, it's a German for build up. But they do build up a whole bunch. So Josh, we're shortcutting, okay? We're jumping way to scandium. I'm going to give this back to Ashley here. Thank you, Ashley. Okay, so we're jumping way ahead. Arsenic, how many electrons? So find a periodic table, you know, one of those, okay? 33, okay. Now I got rid of that list. It might have been helpful, huh, Josh? Oh, well, okay. It's better, though. We'll do all of them. Let's do the long one and then the short one. So every atom puts their, or has electrons, I would say, a multi-electron atoms has a 1s2. But that's only 2 of the 33. 2s2, 2p6, and then probably we kind of already know 3s2. So then what's going to happen if we keep going? So remember that list that was right here? 3p6. Now, where are we at? You can count 6 and 2 is 8. You can count those. It's kind of irritating. I would find a periodic table. This is kind of an oldie. I should get a better periodic table to hold this up. But anyways, when you want to find it on the periodic table, so scandium is right, not scandium, arsenic. It's right there, okay? What you want to do is see that there's some major patterns here. So I'm going to just draw this quick for Josh's benefit and maybe anybody else out there who else needs it or needs a review. This is a tiny set. That should be bigger than that, but I don't care at this point. Okay. So you have 1, 2. Oh boy. Slide this up. 1, 2, 3. No, that's not right. Hang on. 1, 2, 3, 4. 4's got to kind of line up like right here. Okay. And my students have this again already. This is called the S block. So it's going to be 4s, 5s, you know, that kind of thing. So 5, 6, 7. These are really bad. So then this is going to be like a 4s, and then this is where the 3d is, and then this goes back to being a 4p. 1, 2, 3, 4. Okay. So keep that in mind, and then when you get down to here, you'll have 5 and then 6. I can even just add another section at the bottom here. So keep in mind, where are we going to go after a 3p? So this is the 3p right here. This was the 2 or 3s. Goodness gracious, this has been long. This is 2s. This is 1s. This is 2p. Josh, I'm trying to help you here. Okay. So then where are we going after the 3p? 4s, right? But where's arsenic sitting? Isn't it like somewhere in here?
Yeah.
Okay, so we're going to get into that 4p area. So 2. So you can count these, and you can see where we're at. Right now, I got a really smart counting student. What are we at? We're right here. So total of, I have a periodic table over here. Yeah, 20, right? And then we go through here, we get to zinc way over here, which is 10 more, because the D will hold 10, which is 3D 10, just enough room. 4P. Now be careful, find where it is in the 4P, because I hope that you kind of realize if you've done this before. 1, 2, 3, 4, 5. Oh, there, looks great. 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5. I gotta add one more. Let's do it like this. 1, 2, 3, 4, 5, 6. Oh no, that was right. It was. I had it right. False alarm, people. 1, 2, 3, 4, 5, 6. Okay. So where is arsenic in that position? Right here, right? Isn't it sitting at this point? So what you'll say is that this is a P1, P2, P3, P4, P5, and P6. Careful though, that's an S. So Josh, the short story is it ends with a 4P3. He's shaking head. Good. Okay. But this is annoying. Well, let's take all of this and use a noble gas. So what is all of that in a noble gas notation? Argon? Are we all sure? Recording this live. 4s2, 3d10, 4p3. Now be careful. They're going to get you. How many valence? Yeah, 5 total valence. Which electrons, probably with photoelectron spectroscopy proof, which ones would probably be taken first? Easiest, per se. The P's, okay? Now, we don't have to worry about that, but what are some predicted charges for arsenic? We're going to bonding soon. We're almost there. Chemical bonding, intermolecular forces and intra-bonding versus forces between molecules within. Do you guys notice that arsenic has predicted charges of, or oxidation states of, 3 and 5? Is that a true statement? You're one of my students, I hope so. Yeah. What are they losing? Yeah, they're losing the 3 and then maybe the 5.
Oh.
Mind blown. Oh my goodness, Eureka, we got it. Okay, now could we do a quantum number for some of the P's? Sure, I'm not going to do that, but again, you could. So we've got charges that are possible. These are the electrons that are going to end up being removed. Could this be part of a covalent bonding? Maybe because it's in the metalloid area, but generally we think arsenic is going to have a cation charge and be ionically bonded, or it could be metallically bonded. So 3 and 5 are predicted. That's kind of what we're going to next is ionic versus covalent bonding versus metallic bonding. Now we know where the electrons are. That's going to predict what kind of things that these little atoms with their energies are going to end up losing or gaining electrons, getting bigger or smaller. I'm just going to ask really quickly. Let's just do one more, Josh, because we're going to go to a tough one, okay? We need to sneak one that not only is it past or in, like some people pick the next one, like it's in the F, one of the F block. The F block is on the lower, it's the lanthanides and actinides. What I'm going to do is pick, not that, because I think that's obvious, but pick one that's past it and see if you're going to forget. So let's do polonium. Now, we are not doing the whole configuration for polonium. That's insane. So first off is how many electrons does it have? So find your periodic table. Okay, 84. Look for the nearest noble gas, kind of go back around and find the nearest noble gas we can use. So for polonium, it should be xenon. So it's going to point. That's what my students are seeing. It's right there. You can't use radon. You got to go back to xenon. Okay. Next, make sure that you have all the electrons accounted for. I kind of even say make a little count. How many does xenon have? 54. Okay. So when we add up all the electrons, it should get to 84. So what's after xenon? So if you have your periodic trend that I just erased. Yes, 6s2. Now it's common students forget the next one. So it's 2 more. It's 4f. Yes, I don't think AP students should forget that, but they do. Okay. So that's 14 more. And then where does it go after that? So this would be energy level. It's weird. Like it fills 6, and then we're jumping back to 4. That's just the way it is, people, okay? So it's putting out some 6s's, and then it's going back in and filling the f's. I'm not drawing what an F orbital looks like. We're not doing it. The only thing I will tell Josh especially, a 4f makes you have 1, 2, 3, 4, 5, 6, 7. Because it can fit 14 total. So that means if you were doing those quantum numbers, they would range between -3 and 3. And so an F is going to have 3 as sort of one of the quantum numbers. And then M sub L will be the -3 to the +3. All right, let's not worry about that. Let's keep going. What else? Where do we got to get to? 5D. Yes, don't forget you'll go back through the 5D. That's 10 more. How are we doing? We're getting there, right? And then where does it end? So polonium again. Is it in the P block? 6P. Yeah, it's over here. Okay. And it's going to be 6P and then 1, 2, 3, 4, right? Count over. So then, Josh, what you would do if you really were wanting to check, you'd add these up. Okay, so if I add these all together, these are the total electrons, does that give me 84? It does? Okay, good. So then you kind of know you didn't skip anything. I'd recommend that. All right. Sayonara. That is another 30, 40 minutes. Session 3 is coming. I think we're all going to take a nap for 2 minutes. And then we're going to go to Vesper theory, do some ionic bonding, but you're going to have covalent, molecular covalent network, ionic metallic bonding. I think I said them all. And then we're going to talk about intermolecular forces, which are hydrogen bonding, London dispersion, in no order here, people, dipole, and then the elusive polarizability of the LDF with lots of electrons. What in the world does that mean? So that's next. Bye. See you later. If anybody's watching. Remember, 1,000 subscribers, I can use my phone. That's nice. Subscribe, please. I hate using this thing.